Hey guys, today we're talking about conic sections in polar coordinates. But before we can do that, I need to talk about something called eccentricity. This is a picture that I found on Wikipedia because I liked the picture, so that's why we're on Wikipedia right now. Okay, so anyway, these are the four types of conic sections, right? Circle, ellipse, parabola, hyperbola. So there's something that we talk about with conic sections called eccentricity, and it's basically how far away is the conic section from being a circle. So a circle has an eccentricity of 0 because it's a circle. It's not far away at all from being a circle. The next closest thing to a circle is an ellipse. So if the eccentricity is between 0 and 1, that's going to be an ellipse. So 0 is a circle, 1 is going to be a parabola. Anything in between that is going to be an ellipse. Greater than 1, and we have a hyperbola. If you go out to infinity, you're getting closer and closer and closer to a straight line, which kind of makes sense, right? You can kind of envision your hyperbola sort of flattening out more and more until you get to a straight line. So as eccentricity goes to infinity, we're going to get a straight line. So it's the distance from being a circle. The Wikipedia describes it as decreasing curvature, right? Which kind of makes sense. Whoops, I think I clicked on it. Anyway, so yeah. So that's basically what I wanted to talk about with this picture, is sort of that visualization of you're getting further and further away from being a circle. All right, let's go back to the book. So you're probably thinking, what does that have to do with polar coordinates? I'm getting there. So we know that a parabola has a directrix, but there's kind of a imaginary directrix that all of the conics have that's used to calculate the eccentricity. That's not really important for what we're doing, but what is important is that your book refers to a directrix, to the location of a directrix, regardless of the type of conic in this section. So I just want you to know that it's just a line that's used to calculate the eccentricity. And with the parabola, it is the directrix, but the others don't really have a directrix. So if that confuses you, that's why. Personally, I think they should have chosen a different name for it, since it's confusing to think of an ellipse or a hyperbola having a directrix, but here we are. So in the questions, when they're asking you to find the directrix, it's that sort of imaginary line, which we'll talk about, and it's very easy to find with the information that we're going to be given. But yeah, that's what it is. Sort of an imaginary line that for the parabola really is the directrix. Anyway, so your book goes into a whole explanation of how to find the eccentricity. I'm not really going to go into that. I care more about the equations for the polar form of a conic and how that relates to the eccentricity. So these are going to be our two forms of the equation with a focus at 0. Or at the origin, I should say. So the focus is going to be at the origin of our polar coordinate system. So it's going to be there at the pole. Yeah. So one of the foci. Doesn't really matter which one. Actually, yeah. It's going to have a focus at the origin. If it's an ellipse or hyperbola, it has two foci. That doesn't really matter. What matters is that one of them is at the origin. So these are what the equations are going to look like. So you're going to have and it doesn't matter which conic it is, the equation is going to look like this. We're going to talk in a second about how we figure out which conic it is. Well, we figure out which conic it is by figuring out what E is, because as we talked about already, if E is between 0 and 1, then it's an ellipse. If E is 1, it's a parabola. And if E is greater than 1, it's a hyperbola. And of course, if E is 0, it's going to be a circle. This says or equal to with 0 because this book counts a circle as a type of ellipse and doesn't differentiate. I like to differentiate. A circle is a type of an ellipse, but it has its own special properties, as we've talked about previously. So I like to separate it into 4 categories. The book doesn't. It is what it is. Anyway, so if the directrix, whatever that may be, is vertical, then you're going to have cosine in the equation. So another way to think of that as if the parabola opens up left and right, then it's going to have cosine. If it opens up and down, it's going to have sine. And so that's going to be the same with hyperbola, right? If it opens right and left, it's going to be cosine. If it opens up and down, it's going to be sine. Same with an ellipse. If it's longer in the x direction, that's going to be cosine. If it's longer in the y direction, that's going to be sine. And yeah, so then you have E times P, where E is the eccentricity and P is the distance from the origin, right, to that directrix. So, which is thus the x equals plus or minus P. So it's going to be distance from the origin, which remember is a focus, to that imaginary directrix. And then, yeah, so that's basically all you need to know there. So then if we want to identify which conic we have, so here's an example of that. So for this one, if I want to know which conic this is, well, I know that if this is 1, it's not right now, but if this is 1, then this is EP and this is E. So I need to get this to be 1. So I'm just going to multiply top and bottom by 1/3, right? So to get this to be 1. And if I multiply top and bottom by the same thing, I haven't changed anything. So I'm just going to multiply top and bottom by 1/3. So I'm just basically dividing everything by 3. So I have 2 on top, and I have 1 plus 2 over 3. So now that this is 1, this is E. So if my E is 2/3, then this is an ellipse, because that's between 0 and 1. So this is an ellipse. And I can figure out what P is, because this is EP. So if I divide it by E, right? If I divide it by E, so 2 equals EP. So if I multiply 2 by 3/2, then I figure out that P is 3. P is 3. So that's going to be the distance to my directrix. So in this case, it was sine, right? So if sine is up and down, so my directrix is going to be y equals, it's going to be horizontal, so it's going to be y equals, it's an ellipse, right? The plus on the plus here, so the plus here, plus here is going to correspond with the with P also being positive. So it's just going to be y equals P. So if for this one, for example, it's going to be y equals negative P. This one is y equals positive P. This is going to be x equals positive P, because this is cosine. Those are the equations for that imaginary directrix that I was talking about. So the equation for the directrix on this one is going to be y equals 3 because that's what P is. P is 3. So y equals 3. So let's look at the next one. So the next one, we have a 4 here. So we just multiply top and bottom by 1/4 because, again, what we want here is 1. So they've done that here. So 5/4 is more than 1. So this is a hyperbola, right? This is a hyperbola. And then I can use the fact that this 3 is E times P to figure out what P is. So P is 12/5. And so I get that my directrix is going to be x equals 12/5. X because it's cosine, positive because this is positive. So let's look at C. C, we have a 2 here, so we just multiply top and bottom by 1/2 because we want a 1 here. So we get that E is going to be 1. E is 1. So this is a parabola, which means in this case the directrix is real. And this is negative, so and this is sine, so we're gonna have y equals negative P. We have 7/2 on top, so that equals EP. E was 1, so P is gonna be 7/2. And so our directrix is at y equals negative 7/2. So that essentially what we just did, those 3 sections, is what they're asking you to do when they ask for what type of conic do you have and what is the directrix. So we're going to do some examples of some other things in the next couple of videos. So I will see you there. Let me know if you have any questions, etc., etc., and I will see you soon. Bye.